Kubernetes provides multiple built-in APIs for the declarative management of your workloads. In this video, we'll cover all of them. Also, we'll talk about differences between a standalone application, container, and a pod. Additionally, we'll cover init containers and sidecars, as well as extending Kubernetes with custom APIs. Let's start with the application. The app can be a REST API that represents the logic tier in the common three-tier architecture. It can populate your website with existing inventory or register new users. The database application from the data tier can also be deployed in Kubernetes. Your application can be a part of the data processing pipeline. Many companies use messaging systems such as Apache Kafka to decouple different parts of their system. So one application or a device can write data to Kafka, while another subscribes to that topic, reads the data, and performs some kind of transformations. It could also be a machine learning model that you train in Kubernetes using distributed functionality, or by simply deploying that model in Kubernetes as a REST API. Today, most companies try to leverage Kubernetes for almost everything they develop. To create application, you can use any language you want, such as Java, Python, or Rust. In this example, we use Golang to create a simple REST API based on the Fiber framework. The source code for all the examples is available in my GitHub repo. Traditionally, companies ran applications on physical servers. One issue with that approach was if multiple apps were run on the same server, one application could consume all the resources, such as CPU, memory, or even network bandwidth, and other applications could underperform. To solve that issue, virtualization was introduced. Virtual machines provide a level of isolation between different applications while sharing the same hardware. It not only improved security, but also allowed for independent scaling of these VMs. Additionally, you can package all the dependencies inside the VM and run it on the physical server. The problem with this approach is that VMs are full machines that include operating systems, which means there is a significant cost associated with running the VMs themselves. To solve that, containers were introduced. Containers are lightweight VMs that share the same operating system while still providing isolation between applications. Similar to a VM, container has its own file system, share of CPU, memory, process space, and more. You can also package all the dependencies inside a single container image. The start time of a container much quicker, which means you can scale up and down your application more efficiently. Additionally, it's cheaper to run containers than VMs, since they share the same operating system. To package your application and run it as a container, you need to create a container image. In this example, we use a multi-stage build to reduce the size of the final artifact. The smaller the image, the less time it takes for Kubernetes to download and run it. First, we use Golang as a base image. Then we download all the dependencies and build the application binary. In the second stage, we take a much smaller distroless image provided by Google, copy the binary, and define entry point to start the app. Usually, we use a Docker client to build container images and then upload them to a remote repository, such as Docker Hub or AWS ECR. However, you can use other tools such as Kaniko or Podman to build images. You don't have to use Docker at all. Also, Kubernetes recently deprecated Docker as a runtime, and typically we use containerd to run those images in the Kubernetes cluster. Now, Kubernetes doesn't run containers directly. Instead, it has abstraction layer called a pod. Pods are the smallest deployable units of computing that you can create and manage in Kubernetes. For example, if you want to run your app in Kubernetes, at the very least, you would need to build a container image for your application and wrap it in the pod. Then you would use kubectl apply to deploy your pod to Kubernetes. Just keep in mind that pods are usually not created directly. Instead, we use other workload resources, such as deployments, stateful sets, and other objects. A single pod can contain one or more containers with shared storage and network resources, and specification for how to run containers. The shared context of a pod is provided mostly by Linux namespaces and cgroups. For example, we use resource requests and limits, which are based on cgroups, to isolate how much CPU and memory each container can use in the pod. If you don't define those, you can face a similar issue where one pod consumes all the resources provided by the underlying hardware, and all other pods will suffer and underperform. Also, a pod can have a shared volume, and all containers can use it to share data with each other. A volume allows data to persist between pod restarts in case your application crashes or you deploy a new version of your app. Additionally, a pod is assigned unique IP address, and every container in a pod shares the network namespace, including the IP address and network ports. Inside a pod, containers that belong to the pod can communicate with one another using localhost. If a container wants to interact with a container running in different pod, it can use IP networking to communicate. Another useful feature is ability to define health checks for each container in your pod. For example, your app can provide a health or status endpoint that returns a 200 HTTP response code if it's healthy, and optionally some kind of JSON payload in case your monitoring system does not support status codes. The health check is used to ensure that the pod is ready to accept traffic before Kubernetes adds it to the pool. Health checks are also used to perform updates. Kubernetes will only proceed with a rolling update if enough pods are marked as ready. Pods in Kubernetes cluster are used in two main ways. First and most common approach would be to run one container per pod. In this case, you can think of a pod as a wrapper around a single container. Second approach would be to run multiple containers that need to work together inside a single pod. Usually, we have a main application and a helper container that we call a sidecar. One example would be a container that acts as a web server for files in shared volume, and a separate sidecar container that updates those files from the remote source. Another example would be a service mesh such as Istio. You have a main app and a proxy sidecar that intercepts all the network traffic to add additional functionality, such as traffic management, which you can use for canary deployments. It may be mutual TLS to secure communications between your services in Kubernetes, and many others. You need to be very careful when deciding to run multiple containers inside a pod. If you need to scale your application horizontally, which means providing more overall resources by running more instances, you can only scale the pod as a unit. This approach can lead to wasted resources if one of the containers has very low usage and you scale only because the other container cannot handle the load. Besides running containers side by side in the same pod, you can run containers before the main app container starts. These are called init containers. Unlike main containers, init containers always run to completion, and init container must complete successfully before the main container starts. One common use case for init containers is to run a script that blocks until certain preconditions are met. For example, if your app has a dependency on a database, init container will block the start of the main app until the database is ready to accept connections. Besides that, we can also use init containers to configure the network stack and populate data in the volume for the main workload of the pod. For example, we can clone a GitHub repository into shared volume. Another example is Istio, a popular open source service mesh. It uses init containers mechanism to configure the network stack of the pod. Specifically, Istio deploys init container to configure the IP tables of the pod, intercepting all incoming and outgoing traffic of the main application container. Alright, let's say we have an application that we want to deploy to Kubernetes. Let's define a pod object to deploy it. The first problem you'll face when using a pod object is scaling your app. Let's say you want to run 5 replicas. You would need to create 4 more pod objects and apply them to Kubernetes. But what about 20 or even 50 replicas? At this point, it becomes unmanageable. The second issue arises when you want to upgrade your application, you would need to manually update the image tag and apply each pod one by one. If you update all pods at the same time, that will lead to downtime. Therefore, you might want to do it maybe one by one, or at least update only a few pods at a time. Another issue is that most of the pod template fields are immutable. For example, if you need to adjust the resource requests or limits, which is a very common task, you would need to delete the pod first and then create a new one. The same applies to health checks and other fields. Also, Kubernetes is dynamic in nature. You constantly adding or removing nodes from your cluster, as well as upgrading existing nodes to new versions. In this scenario, if a pod is evicted, it will never be rescheduled again, which can lead to all sorts of problems and possibly application downtime. To solve all of this, Kubernetes introduced some level of abstractions. The first one we'll talk about is a deployment object. You simply describe the desired state, such as how many replicas of your application you want to run at the same time. And the deployment controller will make sure that the desired state matches the actual state. If for some reason a pod fails or gets deleted, the deployment controller will reschedule it. The second most common use case for a deployment is to upgrade your application. The default strategy is rolling update. This approach allows you to upgrade your application with zero downtime by incrementally replacing all pod instances with new ones. You can adjust how many pods can be down at any given time and how many new pods should be created. This approach is most commonly used in production environments. Now, there is another less common strategy, which is called recreate. In this case, the deployment controller will terminate all existing pods first and then create new ones. This approach will most likely lead to downtime. It is commonly used in development environments, when you need to quickly deploy a new version and may not have enough room for multiple pods. I have another video explaining common deployment strategies in Kubernetes. Another use case for this approach is with deployments that attach volumes with read-write-once access. For example, with Grafana, if you try to perform a rolling update, it will be stuck because the deployment controller would try to attach existing volume to a second pod, which is not permitted. In this edge case, you can use recreate strategy. The deployment object itself doesn't directly run pods. Instead, it creates a replica set, which is responsible only for keeping a specific number of pods running. A deployment is a higher level concept that manages replica sets and provides declarative updates to pods, along with many other useful features. You can create a replica set directly in the cluster, but it's not possible to perform a rolling update with only a replica set. In this case, you would use a deployment. If you want to learn how to expose your application to the outside world, you can watch this video. The deployment object works perfectly with stateless applications that can be horizontally scaled and do not persist any data. We often use a horizontal pod autoscaler to dynamically scale up and down your application based on the load. You can refer to this video to get detailed and practical explanations on how to autoscale Kubernetes pods and nodes. If your application maintains some kind of internal state and saves it locally on the disk, when the pod gets rescheduled, your application can lose all its data. Most cloud providers allow you to create persistent volumes with read-write-once mode. You can think of it as a single volume being attached to one pod at a time, establishing one-to-one relationship. Technically, read-write-once means that the volume can be attached to a single node, and if your pods run on the same node, it's still possible to attach one volume to multiple pods. However, in production, where we run hundreds of nodes, you should never rely on this behavior, even if you can force pods to run on the same node with pod affinity. But this approach is considered anti-pattern in Kubernetes, since if the node goes down, which frequently happens in Kubernetes, all your application instances will go down at the same time. With read-write once, we almost always use a deployment with a single replica count. The perfect example would be Grafana. You only want to run one instance, and if your pod gets rescheduled, you don't want to lose all your dashboards. To resolve this issue, many cloud providers allow you to create read-write many volumes based on specific file systems. For example, in AWS it would be EFS file system. In this case, you can attach the same volume to multiple pods. A good example of this might be a WordPress, where you run WordPress and a database and share the same volume. If you share a single volume across all your pods, it can become a single point of failure. Also, for high availability, you would want to spread your pods across nodes deployed in different availability zones in the cloud. However, this could be problematic because you cannot attach a volume to a node located in a different zone. Now, if your application doesn't need to share any data with other applications, the most logical approach would be to create a dedicated volume for each replica of your application. If you decide to use a deployment object, you would need to create as many deployment objects as you want replicas of your application along with persistent volume claims. You can immediately see the problem. If you want to scale up or down, it's not enough to edit the replica field. You need to create or destroy both the claim as well as the deployment. To solve this issue, Kubernetes introduced the StatefulSet object. It can dynamically, based on the number of replicas in your specification, create volumes using the common volume claim templates block. For example, if you have 3 replicas, it will create 3 volumes and attach them to the pods. The same applies if you have 20 or 50 replicas. To scale up, you only need to adjust the replica count or use horizontal pod autoscaler. It also ensures that the volumes are created in the same availability zone where the pod will be running. The second important feature of the StatefulSet is the stable network identity for each pod. For example, if you create a deployment object with 3 replicas, there is no practical way to target individual pod. Usually, to load balance traffic, we create a service object with round robin, which randomly routes requests to the pods. What if you actually want to be able to send a request to a specific pod? One example would be Apache Kafka. Let's say you have deployed a 10-node cluster in Kubernetes, and you have a few topics with replication in case one broker goes down, so you won't lose the data. A topic consists of partitions, and each partition has a leader and replicates that partition to other brokers. Now, when the client sends a request to read data from a topic, Kafka returns the broker's hostname with the leader of that partition, allowing the client to connect directly to that broker. Therefore, unless you have a stable network identity for each broker, or a pod in this case, it's not possible for the client to connect to a specific broker. StatefulSet actually provides this functionality by creating headless service. You can access each individual pod using its DNS name. There are some use cases where your application does not need to persist data, but requires only a stable network identity. So you can use StatefulSet for that as well. It's impossible to develop applications without any bugs. Once in a while, we may need to debug the application running in production or your development environments. When we deploy the app to Kubernetes, most of the time we configure the app to write logs to standard output or standard error. Runtimes such as containerd would scrape those logs and store them locally on the node where the pod is running. If you have hundreds of nodes, it's possible but very time-consuming and not convenient to SSH into each node and read the logs. To make it more convenient for developers and SREs, we typically deploy a logging agent such as FluentBit on each node to collect those logs and send them to a centralized place. It could be Elasticsearch, CloudWatch, Grafana Loki, or any other database you prefer. To deploy a single logging agent on each node, you can use deployment or StatefulSet along with pod anti-affinity. The problem arises when you scale up or down your cluster. You need to edit the replica count to match the number of nodes you have. If you forget to scale your logging agent deployment when scaling down your cluster, pods will be in pending state, and you'll receive an alert from your monitoring system. To solve this, Kubernetes introduced a Daemonset. Its job to run a single pod on each node in your cluster. If you scale up your cluster, the Daemonset will deploy more pods. If you scale down, the Daemonset will remove the extra pods. Another common use case for the Daemonset is to deploy a storage agent that abstracts away local node disks and provides them, for example, as object store and distributed file system. Examples would include Rook or Ceph. Also, some applications such as Kafka require fast local SSD disks. For that, we use local persistent volumes. We would deploy a storage agent on each node to create abstraction layer on top of local disks and use them in the volume claims. And of course, we use Daemonset to run monitoring agents. You would deploy a node exporter on each node to collect CPU, memory, network, and other metrics specific to Kubernetes nodes. Also, you would deploy the CI Advisor agent on each node to collect container metrics. This would include the same CPU, memory, and network metrics, but related to containers. These are the most common use cases. Since almost all Kubernetes clusters have some kind of Daemonsets, we typically try to use larger instance types in the cloud to reduce the number of agents we need to run. For example, if you use a node with 2 CPUs and a monitoring agent can take half of that. So a more cost-effective approach would be to use a node with, let's say, 16 CPUs, and your monitoring agent will still only take the same 1 CPU. Therefore, it's just more cost-effective to use larger instances. The last thing I want to mention is that your Daemonset does not ignore taints by default. For example, you may have different node groups in your cluster. Some use GPUs to train machine learning models, others use spot instances, and all of them would use taints to repel pods that are not supposed to run there. You could list all tolerations in the Daemonset specification, but most of the time we want to ignore all taints. To do this, you would use the following syntax. To test this out locally, you can create a multi-node minikube cluster and apply one of the Daemonsets from the examples. Let's talk about a different use case. Let's say you developed a new feature for your application and it requires you to add additional column to your database table. Before deploying the new version of your application in production, you would need to run a database migration. You could create a single pod to run this migration. However, once the database migration is finished and the container in the pod exits with a successful code, the pod doesn't differentiate between a successful exit and an error exit. It will restart the container regardless. After a few restarts, your pod could be in crash loop backoff state, potentially triggering alert. Most migrations can be run multiple times. After it finishes successfully, it will not modify the database schema again. You can wait, check the pod's exit code, and delete the pod afterwards. However, this approach is not the most convenient, to say the least. Another issue could arise if the migration takes a significant amount of time. The node where the pod is running could be removed, or something else might happen to the pod. Therefore, you want to ensure that the pod runs to completion at least once. To solve this issue, Kubernetes introduced job object. The main use case is to create one job object in order to reliably run pod to completion, which is exactly what we want for migration. If you use Helm charts to deploy your in-house built apps, you can use Helm hooks to automate job creation at certain points in the release lifecycle. There are some advanced use cases that allows you to run parallel jobs and create work queue. For example, open source frameworks such as Airflow use jobs to run distributed data pipelines. What if you want to run a job every day to backup a database such as MongoDB or Postgres? For that purpose, Kubernetes introduced a CronJob. You can use it to backup a database or generate create a report. It follows the same syntax as the crontab file on Unix systems. For example, this CronJob will run every 6 hours, and another one can be configured to run every day. So far, we've talked about built-in APIs. However, you can leverage Kubernetes, especially its reconciliation loop, to extend it with your own declarative APIs. For example, suppose you have a distributed stateful application that needs to be constantly maintained. You might need to backup your application and, most importantly, be able to recover it if something happens with the Kubernetes cluster. Also, you may need to perform rolling upgrades and verify that the cluster is healthy after updating each node. My point is that you may have many manual operations that needs to be performed to maintain the application. By creating operator, you can automate all these manual tasks in the code. Most of the time we use Golang to create operators, but Kubernetes SDKs are available in other languages as well. For example, instead of using StatefulSet to deploy Apache Kafka, you can create operator and use a custom API such as Kafka cluster. First, you create a schema for the custom Kubernetes API and register it with Kubernetes. Then, you would develop a Golang application and deploy it in Kubernetes as well. When a user wants to create a Kafka cluster in Kubernetes, they would declare a custom resource object and apply it to Kubernetes. The data will be parsed and saved in etcd cluster. Then, Golang application, which we call the operator, will detect the new Kafka cluster resource and reconcile it. I think the Prometheus operator is one of the most popular open source operators. It not only manages the lifecycle of the Prometheus server by deploying and removing it from the Kubernetes cluster, but it also offers custom APIs such as Service Monitor, which help to register new targets with Prometheus. It converts the custom API into native Prometheus configurations, then updates the secret or config map and hot reloads Prometheus to register new targets. Another popular framework based on Kubernetes is Crossplane. Instead of managing resources inside the Kubernetes cluster, it manages cloud infrastructure, similar to Terraform. However, due to the reconciliation loop of Kubernetes, Crossplane can automatically detect and correct the drift. Terraform can also detect the drift, but only when you explicitly run it. I have a tutorial if you want to learn more about Crossplane and how to use it to manage infrastructure in AWS, including creating a VPC and EKS from scratch. Thank you for watching, and I'll see you in the next video.